Assalamualaikum and hi everyone. So let's continue to look at the force convection across a single sphere. So um, the flow across cylinders and spheres is frequently encountered in our daily life. Okay, for example, for the cylinders, one very common example is the tubes in the shell and tube heat exchanger where it evolved. Okay, so heat exchanger will consist of many, okay, several tubes. So inside the tubes there is an internal flow, and then outside, outside the tubes there is an external fluid flow over the tubes. Okay, so for the case of heat exchanger, both these internal and external tubes must be considered in our thermal analysis. So for spherical shapes, okay, we can maybe example like soccer, balls or tennis or golf balls, okay, that involve flow over the spherical balls. Okay, now this is an example of our sphere. So we had fluid flowing across the single sphere at constant TB and constant velocity. So in the beginning, okay, since the velocity is low, the Reynolds number must also be lower. So when the Reynolds number is lower, what happen is we can see that there is a layer that nicely wrap the body of the sphere. Okay, however, as time move on, okay, the fluid velocity might be increased. So as the fluid velocity is increased, we started to see that there is some formation of tails here. Okay, that is over time. Okay, I want you to be able to see it clearly. So now we can observe this formation. Okay, this is what we call the boundary layer separation. Okay, so at the back here, the flow regime is turbulent. Okay, because of the higher Reynolds number. Okay, we can see it started to breaking, the layer start to break behind the body of the sphere. So that's why we need to do analysis based on the external flow that flowing past these spherical bodies. So normally, the single sphere is either heated or cooled by any of the fluid that flowing past through it. So the average heat transfer coefficient, which is H, can be predicted by using this equation. Okay, where the Reynolds number, okay, now it's no longer L, but it's actually D because the characteristic dimension of the sphere is diameter. So to calculate Reynolds number, it is equal rho V multiply with D divided by mu. Okay, so as usual, the fluid properties are evaluated at the film temperature. So I hope you still remember the fluid temperature. Film temperature is 1 plus TB divided by 2. Okay, however, this equation is only applies for when the Reynolds number is between 1 to 70,000 and for Prandtl number between 0.6 to 400. Now let's look at example 4. So we are going to use the same condition as in the example for the plate, where air at 180 m absolute pressure and 15.6 degrees Celsius is flowing at velocity of 12.2 meter per second. Predict the average heat transfer coefficient H or the air flowing by a sphere having a diameter. So the diameter of the sphere is 0.051 meter and average surface temperature. This one is the TW. So imagine this is the sphere. So this is the diameter of 51 millimeter and TW, which is the T wall. Compare this with the value of H from the flat plate in turbulent flow. Okay. First step that we are going to do is we have to determine TF, the film temperature. Okay. So how? Okay. By using this formula, so our film temperature is at 48.9 degrees Celsius. Next, with the knowledge of this film temperature, what we're going to do next is find out all the fluid properties from Appendix A33. Okay, you might have to do interpolation. Okay, for example, here I show you this appendix of table A33. So 48.9 degrees Celsius is in between 57.8 and 65.6. So obviously you have to do linear interpolation. Linear interpolation. I'm not sure how you do it, but this is my way. So K Prandtl number and one more is mu. Okay, so please don't forget for the mu value. Okay, since the title had 10 to the power of 5, so your mu final value would be 10 to the power of negative 5, right? So please do interpolation and obtain all this value here. Okay, so I give you the answers of mu B, Prandtl number, thermal conductivity, and also the density. Now, what we're going to do after we get all the fluid properties? Okay, the third step is to calculate the Reynolds number. Why we have to calculate the Reynolds number? Because we have to check whether the Reynolds number satisfy these limitations. Okay, so check the Reynolds number. Okay, so this is not L but D. D multiply with the velocity and rho divide by mu. So our Reynolds number is 3.49 times 10 to the power of 4. So it is within the range of the acceptable Reynolds number that I've shown previously. So we can use this Nelson correlation to estimate H. Okay, the average convective coefficient. So just plug in the value. This is value of D. This is K from our interpolation. And this is Reynolds number and Prandtl number from the interpolation. And finally, you will get the average coefficient as 56.1. Okay, so the example says that compare. Okay, so over the fluid that is flowing across the single sphere had an H value of 56.1. Okay, this is over sphere. Over flat plate is 7.2. Okay, so how to do comparison? So you just say which one is smaller, which one is larger. Okay, so here we can see that the ones that is flowing over the sphere is much smaller than the ones that is flowing over the flat plate. Okay, that's all.